Proof by induction. In this video we look at the process of constructing proofs using mathematical induction, and we look in particular at examples considering pairs of matrices and divisibility tests. Examples considering sums of series will be looked at in a later video. To prove a result about the positive integers using induction, we must do two important steps. The first step is to prove that the result is true for n equals 1. Then we assume that the result is true for n equals k and deduce that it must also be true for n equals k plus 1. Once we have gone through those two steps, we have completed our proof by induction, since we know by step 1 that the result is true for n equals 1. Moving to step 2, we can now say we know the result is true for n equals 1, so step 2 tells us that it is also true for n equals 1 plus 1, in other words for n equals 2. We now know the result is true for n equals 2, so step 2 again tells us that it is true for n equals 2 plus 1. In other words, step 2 has told us that the result is also true for n equals 3. And we can continue this process onwards to any positive integer at all. So let's now have a look at a couple of examples of mathematical induction. So the first one is to prove that the nth pair of the matrix 1, 1, 0, 2 will always be of the form 1, 2 to the n take away 1, 0, 2 to the n for all positive integers n. So our first thing is we must go through step 1. We must make sure that the result is true for n equals 1. Well, when n equals 1, the left-hand side is simply the matrix 1, 1, 0, 2 to the power 1. Anything to the power 1 is simply itself, so we have the matrix 1, 1, 0, 2. On the other hand, the right-hand side of the result, when n equals 1, reads 1, 2 to the 1 take away 1, 0, 2 to the 1. And we simply need to remember that 2 to the 1 is equal to 2, to deduce that the right hand side is equal to 1, 1, 0, 2. So we can see the left hand side of the result is the same as the right hand side of the result when n equals 1, so the result is most certainly true when n equals 1. So we now progress to looking at step 2. We must assume the result is true for n equals k, and we must then go on and deduce that it is also true for n equals k plus 1. So we are going to assume that 1, 1, 0, 2 to the power k is known to be 1, 2 to the k take away 1, 0, 2 to the k, and we're going to try to show that 1, 1, 0, 2 to the power k plus 1 is the same as 1, 2 to the k plus 1 take away 1, 0, 2 to the k plus 1. Now it is a very good idea to have this matrix here as a target matrix. That's what we're trying to show, that 1, 1, 0, 2 to the k plus 1 is equal to. So that is our target matrix as we perform step 2. So there's our assumption. We know that 1, 1, 0, 2 to the power k plus 1 is going to be the same thing as 1, 1, 0, 2 to the power k times by 1, 1, 0, 2 to the power 1. because something to the power k plus 1 is something to the power k times by the something to the power 1. In other words, times by the something. There's the target matrix that we have got. So we've got to try and fill in the gap. We've got to try and show that our red matrices at the top of the page actually ends up equaling so that these two matrices here multiplied together actually equal this matrix here at the bottom of the page. So in order to fill that gap, what we can do is we start off by doing our matrix multiplication. Well, we know that 1, 1, 0, 2 to the power k is equal to 1, 2 to the k minus 1, 0, 2 to the k by the assumption that we're making at the beginning of the step. So we've got to multiply that matrix by 1, 1, 0, 2. Performing the matrix multiplication, first thing we've got is 1 times 1 plus 2 to the k minus 1 times 0, and that just gives me 1. Now moving to the top right hand corner, we have got 1 times 1 plus 2 to the k minus 1 times by 2. Moving to the bottom left hand corner, we've got 0 times 1 plus 2 to the k times 0, which is most certainly 0. And moving to the bottom right hand corner, we've got 0 times 1 plus 2 to the k times 2. Now we need to do a little bit of simplification of this. Top left hand corner, clearly we've just got 1. The top right hand corner of the matrix, we have got 1 plus 2 to the k times 2, take away 2. Bottom left hand corner, we've clearly got 0. The bottom right hand corner, we've got 2 to the k times 2. Now a little bit of thought about indices will tell us that 2 to the k times 2 is the same thing as 2 to the k times 2 to the 1, so that is the same thing as 2 to the k plus 1. Now we're getting very close to our target matrix. The top left entry here is the same as the top left entry here. Bottom left entry here is the same as the bottom left entry here. Bottom right entry here is the same as the bottom right entry here. So the only place we've just got to stop and think about is the top right entry. We've got 1 plus 2 to the k times 2, take away 2. Well, 1 take away 2 gives me minus 1, and we know that 2 to the k times 2 is the same thing as 2 to the k plus 1. So we've now got that all of our working in red eventually gives me that target matrix that I had. So what I can now do is say that if the result is true for n equals k, then the result must also be true for n equals k plus 1. So at this stage, we've shown that the result is true for n equals 1, and we've also shown that if the result is true for n equals k, then it is also true for n equals k plus 1. So we know the result is true for n equals 1. Using step 2, if the result is known to be true for n equals 1, then it is also true for n equals 2. So we know, using step 2 for the first time, that the result must also be true for n equals 2. Knowing that the result is true for n equals 2, step 2 tells me that the result must also be true for n equals 3. And we can carry that process on ad infinitum, so we therefore know that the result is true for all positive integers n. So we've proved the result. In terms of the mark scheme for this question, there would be 1 mark for showing that the result is true for n equals 1. There would then be 5 marks for the working associated with step 2, for deducing that if the result is true for n equals k, then it is also true for n equals k plus 1. And then the final 7th mark for the question would be for making it clear why the two steps, step 1 and step 2, actually means that the proof is valid for all positive integers n. So that's going through the little process of saying the fact that I know the result is true for n equals 1 means I can deduce using step 2 the result is true for n equals 2. The fact I know the result is true for n equals 2 means that I can use step 2 again to deduce that the result is true for n equals 3, and that process can be carried on as far as I want it to be carried. So there's our first example of a proof by induction. For the second example, we are going to use mathematical induction to prove that 6 to the n plus 4 is divisible by 10 for all positive integers n. So as usual, we must start by proving the result is true for n equals 1. If n equals 1, 6 to the n plus 4 is 6 to the 1 plus 4. 6 to the 1 is just 6, so it's 6 plus 4, which is 10. And 10 is clearly divisible by 10, so the result is clearly true for n equals 1. We then progress to step 2. We're going to assume the result is true for n equals k, and prove that it must also be true for n equals k plus 1. So we're assuming that we know that 6 to the k plus 4 is divisible by 10. In other words, we're saying that 6 to the k plus 4 is equal to 10 times x, where x is a whole number, where x is an integer. Now what we've got to start and think about is 6 to the k plus 1 add 4. And we need to show that that must also be divisible by 10. Well, if we think about laws of indices again, 6 to the k plus 1 is the same thing as 6 to the k times 6 to the 1. So that's the same thing as 6 to the k times 6. Or equally well, it's the same thing as 6 times 6 to the k. Now, if we look at the expression that we had a moment or two ago, we were assuming that we knew that 6 to the k plus 4 was divisible by 10. We were assuming that 6 to the k plus 4 was equal to 10 times x, where x is a whole number. We can rearrange that expression here to rewrite 6 to the k as 10x minus 4. Substituting that in, we've now got 6 to the k plus 1 add 4 is 6 lots of 10x minus 4 add 4, multiply the brackets out, that becomes 60x minus 24 add 4, or 60x minus 20. And 60x minus 20 is clearly the same thing as 10 times 6x minus 2. So we are certainly coming out with the fact that 6 to the k plus 1 add 4 must be divisible by 10, provided we are assuming that 6 to the k plus 4 is divisible by 10. So, if the result is true for n equals k, then we have deduced the result must also be true for n equals k plus 1. We've completed step 2 of the induction proof. So, we've shown that the result is true for n equals 1. We've shown that if the result is true for n equals k, then it is also true for n equals k plus 1. Knowing that it's true for n equals 1, step 2 enables me to deduce that it must be true for n equals 2. Knowing that it is true for n equals 2, step 2 again enables me to deduce that it must also be true for n equals 3, and we can carry that process on ad infinitum, so we therefore know that the result is true for all positive integers n. So we've completed the proof by induction. Again, this question is worth 7 marks, 1 mark for doing step 1, 5 marks for the more awkward step 2, and then finally the final mark is assigned for linking step 1 and step 2 and ensuring that you and the examiner understand the proof is complete for all positive integers n. Now this second example can be given an alternative, slightly different formatted solution. All we're going to do is we're just going to let un be shorthand for 6 to the n plus 4, and we wish to show that un is divisible by 10 for all positive integers n. So step 1, prove the result is true for n equals 1. Well, u1 is 6 to the 1 add 4, which is 10, which is clearly divisible by 10, so the result is most certainly true for n equals 1. Let's see how step 2 now looks. So we're going to assume the result is true for n equals k and deduce that it must also be true for n equals k plus 1. So we are assuming that we know that uk, which is 6k plus 4, is divisible by 10. Now, what we are going to do here is we are going to consider uk plus 1 take away uk. If we consider uk plus 1 take away uk, then we've got 6 to the k plus 1 add 4, take away 6 to the k add 4. Getting rid of the brackets, that's 6 to the k plus 1 add 4, take away 6 to the k, take away 4. And clearly the 4's just cancel. So we've got 6 to the k plus 1, take away 6 to the k. Now need our little bit of indices work again. So the laws of indices tell me that 6 to the k plus 1 is the same thing as 6 to the k times 6 to the 1. And 6 to the 1, of course, is the same thing as just 6. So I've got 6 lots of 6 to the k, take away 6 to the k. Well, 6 lots of something, take away the something, simply gives me 5 lots of the something. So 6 lots of 6 to the k, take away 6 to the k, gives me 5 lots of 6 to the k. So, just rearranging slightly, we know that uk plus 1 take away uk is 5 lots of 6 to the k. In other words, uk plus 1 is equal to uk plus 5 times 6 to the uk. 6 to the k is a positive integer, so 6 to the k is certainly an even number. 5 times an even number is certainly divisible by 10. We're assuming that uk is divisible by 10. So I've got uk plus 1 is a number divisible by 10 plus another number divisible by 10. So we can deduce that uk plus 1 must also be divisible by 10. So if uk is divisible by 10, then uk plus 1 is divisible by 10. If the result is true for n equals k, then the result is also true for n equals k plus 1. And then the conclusion of the solution by this alternative method has the same format as every other proof by induction. So we won't go through that again in detail. We've already looked at how the marks went for this question. 1 mark for step 1, 5 marks for step 2, and then the final mark for the explanation linking the two steps together. Proof by induction is a frequently used method of mathematical proof. Within FP1, you'll be using proof by induction to prove results about sums of series, as well as the type of examples that we've been looking at on this revision video. And you'll find an example of a proof by induction for a sum of series on the revision video that has been prepared for sums of series.